Happy Wednesday, you guys. Hope your week is going well. Hang in there. You're almost there. We've only got about a week and a half or 2 weeks left. Almost made it. I'm continuing to pray for you guys. I know you've got a lot on your plates, a lot of last-minute stuff that's coming up. I'll try not to give you guys last-minute stuff as well. Just a reminder, there's no quiz tomorrow. You've got that time off. But we will be going through volumes, and we're going to be tackling volumes today and tomorrow, and then next week on Monday. On Wednesday next week, we're going to do our review for the exam. And then on Thursday, I'm going to actually be there physically, and we'll do a little more review if you guys need it. Plus, there's one last topic that I want to go over, which is on arc length. It's on length of curves. Okay, and we will have a quiz that day, just over some volume, some area stuff. But that's next week, and we'll talk more about that. As you review, if you start looking at the review problems, I think I've already. You've got a review sheet. I'm going to give the review sheet to Ms. Barabo, so she's handing that out for next week's problems as well as the following week's problems. So you'll have those. One thing that I do want to just say about the review problems for the final exam, I'm making those problems optional in the sense that you only need to do the problems that will help you. So there's a lot of problems assigned. I would highly recommend that you don't do them all. There's a lot of problems in there, and they span a number of different sections. But what I would recommend is that as I go over the review next week on Wednesday, you think about, okay, I know how to do those problems. I don't need more practice on those. Or when you look at the problems themselves and you think, I don't need to do that. I feel comfortable with that. My advice is focus in on the problems that you really need the help, you really need the practice on. And the answer key will be there on RedWeb. You can look it up. You'll have access to it. So you shouldn't, if you get stuck, you can take a look at it. But again, my advice when you're studying for this final exam is that you only work on the problems that you really feel like you need the practice on. There's no help to you to be remotely doing stuff that you already feel super comfortable with. Okay? That's about a week away or so at least. Okay, just a review. Chapter 6. We're talking about applications of integration, and particularly length, area, and volume. We talked about area in section 6.1. So this was area between curves. And one of the things that I noted to you is that if I have a curve and another curve, okay, if I give you a couple of curves, the first thing you should always do on these is you should draw what they look like. Okay, so our steps will always draw the region. Then if they don't give you several points to, if they just give you the two functions and they don't give you, do this from x equals 2 to x equals 3 or something, then you need to find the intersections, the intersection points. And the way that you do that is you set the two functions equal to each other. All right, and then you set up the integral. And that's always going to be the integral. Your area is going to be the integral of your height. So if we think of these as rectangles, we've got those rectangles have a height times a width. And if I did it this way, that width would be a dx. And I'm going to go from 0 to whatever that point is. Let's say that point is 5. And I'm always going to take my upper function minus my lower function. Alternatively, instead of cutting it up that way, you could cut it up by thinking of the rectangles going this way. And if you do that, then your width is dy. And you're going to do upper function minus lower function. Remember, upper is this way, lower is this way. So if you tilt your head and you're thinking of it, this would be the upper function. That would be the lower function. And you would go from this point to that point. And you would find that out from the intersections, okay? So that's what we talked about last time. And hopefully today, if you've got a couple of questions, I'll leave some time so Ms. Barabo can answer some of those questions. The other thing that I wanted to do before we move on to volumes is related to the area of a circle, and I wanted to prove the formula for an area of a circle for you. Because this is a critical thing. If you've never seen it before, it's really good for you to see. Okay, so you don't have to take notes on this. It's obviously I'm going to put this on RenWeb. You can watch it again if you want to. I'm not going to make you redo this on an exam. If you want to take notes, you're welcome to. I don't think this is in the book, strangely enough. And you'll see why it's not in the book. But this is actually one of the reasons why we did Chapter 7 before we did Chapter 6, because we're going to need some of the integration techniques from Chapter 7 when we do this. Okay. So let's get the formula for, I'm actually going to start over there. The formula for the area of a circle. Okay, and a circle of radius r. Now that should be, the area should end up being, what is the formula of an area of a circle of radius r? That should be pi times the radius squared. This should be the answer that we end up getting. So let's see if we end up getting that. Okay, so what I'm going to do, a circle of radius r is determined by the equation x squared plus y squared is r squared, right? Remember that from geometry? So that looks like this circle here. And that circle is, if you solve for one of those variables, if we solve for y, you get plus or minus the square root of r squared minus x squared. Okay? The plus or minus is that this upper region right here, this upper function is r squared minus x squared under the square root. The bottom one is negative the square root of r squared minus x squared. Okay. Now I want this whole area. Now I'm going to be lazy and try to make my work as small as possible. So what I'm going to do is notice that this region right here is 4 times the total. So what I'm going to say is that this area, the area that I want of the whole thing, is 4 times this region right here. And what I'm going to do is draw in a sample rectangle there. Let's do it with dx's. So let's kind of do vertical rectangles like we normally started out doing. Okay, and those rectangles are going to go in this region from x equals 0 up until x equals r, right? So we're going to integrate from 0 to r. The height of that rectangle is this function right here, which is the square root of r squared minus x squared, and the width is dx. So that is the setup, that is the integral that we want to do. Okay, that's the area that we're looking for. We want that area to end up being pi r squared. Everybody see how I got that? So now, I want you to turn to the person next to you and say, how are we going to solve that integral? What integration technique are we going to need to do in order to solve that integral? Turn to the person next to you and talk about that. How would we solve that integral? Okay? What you should have said is that the answer, we want to do a trig substitution, right? You see the square root right here. And the trig substitution, if this was 1 minus x squared, we would do x equals sine theta. Because it's r squared minus x squared, I need an r here. So that when I square it, I get an r squared there, and we can pull that r squared out. of that integral, okay? So you should have said, let's let x equal r sine theta. And when we do that, dx is going to be r cosine theta d theta. Okay? Now this is a situation where we have a definite integral, but I'm just going to leave these as in terms of x. I'm going to leave it as x equals 0 to x equals r. And we'll substitute back in later. You'll see why. It'll be a lot easier just doing this. Okay? So let's plug in. We've got the square root of r squared minus x squared is r squared sine squared theta. And dx is r cosine theta d theta. So we're going to go from x equals 0 to x equals r. I can pull that r squared out of both of these, and I can pull it out of the square root, and that becomes an r. And what's left there is 1 minus sine squared under that square root. And then I just rewrite everything else. I have an r here and an r here, so let's pull those out of the integral. Make that r squared. And then 1 minus sine squared is cosine squared, and the square root of that is just cosine. And then I've also got another cosine left here, so what I'm left with inside that integral is cosine squared. All right. So that's where we're at right now. I want you to turn to the person next to you now and say, what do I do from here? And that person should answer you. They should tell you what you should do. What's the next step that I do to do that integral? That's an easier integral than what we had before. How do we solve that one? Okay, what you should see there is we're going to, instead of cosine squared, we're going to sub in the half angle formula, or the double angle formula. Cosine squared theta is 1/2 1 plus cosine 2 theta. Right? And so pulling that 1/2 out, 4 times 1/2 gives me 2 r squared. The integral of 1 is just theta. And the integral of cosine 2 theta is sine 2 theta. But when I differentiate, there would be a 2 that would pop out, so I need a 1/2 sitting there to compensate for that. Okay? So our integral here is, the integral of 1 is theta, and the integral of cosine 2 theta is 1/2 sine 2 theta. And I'm going to again go from x equals 0 to x equals r. Right? So the integral's done. We just need to substitute back. In order to substitute back, this is one of these weird situations where I'm going to have to sub in a formula for sine of 2 theta that you could get from your trig formulas in the back of your book. I'm just going to go ahead and put that in here. Sine of 2 theta is 2 sine theta cosine theta. We'll need it in that form in order to sub back. Okay? So sine of 2 theta is 2 sine theta cosine theta. So now what I do is I go back to my trig substitution here. So sine of theta is x over r, and I'm going to draw my rectangle. Here's my theta. SOHCAHTOA, sine is opposite over adjacent, so x over r. So opposite is x, and hypotenuse is r. And then the adjacent side is, from the Pythagorean theorem, x square root of r squared minus x squared, which is the thing that you see in here. Again, that's our double check. Okay? All right, so subbing in now, theta is the arc sine of x over r. plus sine of theta is x over r, and cosine of theta, so ca, is adjacent over hypotenuse. It's square root of r squared minus x squared over r. And now we have x's, so I can just say x is going to go from 0 to r. Okay. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. Got it? So now let's just sum in. When x equals r, we've got 2r squared times arcsine of r over r is the arcsine of 1, plus, I want you to notice when we plug in r over here, we just get 0. R squared minus r squared gives me 0 here. So that whole term just becomes 0. Minus, when I plug in x equals 0, I get the arcsine of 0. Minus, when you plug in 0 here, when x is 0, this whole term again goes to 0. So a bunch of stuff goes away, which is really nice. And now, we just have to remember what the arcsine of 1 is. So this is the angle whose sine is 1. When the sine is 1, the sine is y. That's pi over 2. Got a plus 0. That goes away. The angle whose sine is 0, that's what this means. That's just the 0 angle. So the 2's end up canceling, and we get, lo and behold, pi r squared. Here's our nice, simple formula from a very complicated calculation. Okay? So that is, now you can maybe trust it more. The area of a circle truly is pi r squared. It's not just because somebody told you it's pi r squared. Okay? All right. So what we're going to do now is we're going to look at volumes over the next 2 sections, so section 6.2 and section 6.3. Section 6.2 and 6.3 are 2 different methods of getting volume. Sometimes one is easier than the other. I mean, we'll figure out how do we know which one is easier to do. We'll look at that later. Now the book calls section 6.2 volumes using the disk method. I do not like the name the disk method because many times you're not talking about disks. So we're not going to call it the disk method. Instead, we're going to call it the slice method. Okay, it's a much more visual way of what it is that we're looking at. Okay? So the idea is you're going to be given a volume, and I'll explain how we get that volume in a second, but you might be given, for instance, a sphere. Okay? So you're given a sphere, and we want to figure out the volume of this sphere. What we're going to do is we're going to imagine, I want you to picture, if you have ever seen, I don't know if any of you have been to the grocery store and seen your parents order lunch meat from the meat counter, and there is a machine that the lunch meat people have where it's this machine and you put the meat in there and you go back and forth like this, and what it does, let me do it this way, you go back and forth like this and it shaves off pieces of the meat by cutting off a small sliver of the meat. Okay, so you have this thing of meat, and what it eventually ends up doing is it shaves off small pieces of the meat this way. We're going to think of doing volumes in that same way by slicing the object up. Imagine taking a knife and going like this and slicing it up. And what you're going to end up with are pieces, in this case if it's a sphere, you're going to get pieces that look like, that have a particular that have a particular geometric shape. In this case, what would the pieces look like if I sliced this up vertically like this? This thing, if I pulled it out, it would actually be a circle with a small width to it, right? So what we're going to imagine doing to get the volume of this object, just like we did when we got the area of an object over a particular region, we cut this up, we sliced it up, and we added up the areas of the various rectangles in this case. Rectangle would be height times width. Here we're going to imagine cutting up this object and adding up all the volumes of the small pieces where, in this case, you'd have a width of the piece, which would be like a dx. And then the volume would be width times area, and the area depends on what kind of object you're looking at. Now, the reason they call this the disk method is many times when you do this slicing, what you end up with are disks. You end up with circles, but not always. And we'll see that as we look at some various examples of these. So the idea is we're going to slice up our object, and we're going to figure out what the volume is of an individual piece, and then add that up from one side to the other in the same way that we added up these rectangles from one side to the other. Okay, that's the overall concept behind what we're going to do here. Okay, so let's look at the region. I'll give you an example here. So let's take the region bounded by the functions y equals x squared, y equals 0, and x equals 1. Okay, and then we're going to rotate that around an axis, which which in this case is going to actually be the x-axis. Okay. So this is the typical kind of volume problem that you're going to see in this section. We've got a region bounded by some functions, and we're going to rotate that region around an axis. Okay, so like before, the very first thing you do is you start out by drawing the region. So we're going to do that here. Let's draw this region. So the region, we've got y equals x squared. You should feel comfortable drawing that. And then we've got y equals 0, which is the x-axis. And then we've got x equals 1, which looks like this. So the region that we want is that region right there. Everybody follow? So the region we're starting with is this region right here that's based on these three equations that we're given here. Got it? Okay. Now that we have that, what we're going to do is we're going to rotate that around the x-axis. So the second step, always do this in 2 steps. It starts to get way too complicated if you do it, if you try to do this all in one picture. Please make sure you use 2 pictures. So once you draw the region, then rotate it and draw the volume, draw the 3-dimensional object. Okay. So what I'm going to do here, this may require some artistic ability, and if you like art, you're going to love this section. If you hate art, you hate drawing, this is going to be an interesting section for you, because we're going to be drawing a lot of circles and a lot of other things, but it may help improve some of your drawing as well. So what I recommend doing, if we're rotating around the x-axis, I recommend, so you can imagine if I took this region and I spun it around the x-axis, what we're going to get is something where the top is a point. Well, if I'm thinking of looking at it this way, the top would be a point, and the bottom would be a circle, and it would look kind of like a little cone that has a little bit of a swoop to it, right? The way that I draw that here, the easiest way to draw this type of thing is to first draw the region. Okay, so the region looks like this. Just draw the region, not all the other functions, just draw the region. And then I draw that region rotated around the axis on exactly the other side, 180 degrees on the other side. So if I rotated this around, if I spun this around, I spun it 180 degrees around, it would go down here. Right? So that's the other side of that. Let's see if I can make that a little better. So that's, and now, if you now imagine it spinning, what's going to happen is that this bottom part is going to become a circle that's going to come out here three-dimensionally. So the way that I draw that is I draw kind of an oval here that looks a little bit three-dimensional. Do you see that? So that's the resulting volume that's going to happen when I take this region and rotate it. It's going to spin around and it's going to have some stuff out here, some stuff in the back. It's going to come out like that, right? So now what we're going to do is we're going to draw a sample slice, and the way that I do that, so that we can add this up, is I imagine slicing it over here first. Okay, I imagine slicing that over here first. I'm not really getting very good color here. Try this. See that a little better? I imagine slicing it there, and if I sliced and rotated, what would happen is that slice would look like this. Right? In other words, that slice would be a circle, be a disc. So what I now need to do is I need to do what I did before, which was set up the integral and then integrate, but I've got my picture that's going to help me. All right. Now, my volume here, just like with my areas, the volume is going to be, I'm going to integrate, but what I'm going to do is I want to integrate these slices moving from one side to the other. Okay, in the slices, I want the volume of the slices. I want to add up the volumes of the various slices. Now, the slices are going to have an area right here that we call a cross-sectional area times a thickness. And in this case, that thickness is dx, right? Just like our thickness over here was dx. Our thickness here is going to be dx. And x is going to go, in this case, because of the way this was set up, x is going to range from 0 to 1. So I'm going to put in my limits here from 0 to 1. And the area is determined by what kind of shape this is. Now this is a circle, so the area of that circle is going to be pi times the radius squared. And the radius of that circle, you can kind of see it. This is why it's really super important to have a good picture here. The radius of that circle is this height, which is the height of the function here. So that function is x squared. It's minus 0 if you want to think of the bottom. But that radius, that height, is x squared. So what we're going to get here is this is the integral from 0 to 1 of pi times my radius is x squared, and I'm supposed to square that. That is the setup for my integral. Got that? So that is what I need to, that is what I'm trying to set up there. Again, I want to add up the volume of the slices, which is an area times a thickness. My thickness is dx. My area is determined by what kind of thing that is. In this case, that's a circle, so I need pi times the radius squared, and the radius comes from the height of the function. So if I were to finish this problem out, we'll pull out the pi, and x squared squared is just x to the fourth. So we want 1/5 x to the fifth from 0 to 1, and that's just going to be 1/5 pi. That's the volume of that thing. Okay. We'll do a couple more examples, and this will start to make a little more sense once you get this under your belt, okay? Okay, let's try another example here. Let's take the region bounded or enclosed by the function y equals the square root of sine from x equals 0 to x equals pi. And then let's rotate that around the x-axis like we did before. Okay? So again, the first thing I'm going to do is I'm going to draw my region. So in this case, you may want to use a graphing calculator. If you know what sine looks like, the square root of it is just going to be, it's going to be a little bit different. You can put this in your graphing calculator, but essentially this is going to look quite a bit like sine. Okay, that's the function from 0 to pi. So here's my region. This is the function square root of sine. And then what I want to do is rotate that around this x-axis. I want to spin it this way. So you can imagine it's going to look a little bit kind of like a, it'll be round around here, and then it'll kind of pinch to some ends at the very end here. So let's draw that. Let's draw the same region up here, and then a copy of it down below. Okay. And again, the part in the middle is what's going to what's going to go around. So it'll look something like that. All right. So again, the way that you get the three-dimensional version is you draw the top part, flip it around 180 degrees, that gets you the bottom part. And then for the parts that are going to actually make a circle three-dimensionally, you can draw a circle by drawing an oval that will kind of give it this three-dimensional look. Okay? So we've got our volume now. Now I want to draw a sample slice and see what that looks like. So if I draw a sample slice here, kind of at a random place, and notice that this is going to be dx. That sample slice, when I rotate it, is going to look like this. And it's going to have a thickness that I'm drawing in here. That thickness is dx. And when I pull that out, that's again obviously a circle. So that'll help me with my volume calculation. So my volume of my region now, I'll let you catch up here. The volume of my region now is going to be the area, the cross-sectional area of that slice times the thickness. It's the volume of that slice. Okay, and the thickness is dx, which tells you everything here needs to be in terms of x. You'll notice x is going from 0 to pi, so I fill that in over here. And since this is a circle, the area is going to be pi times the radius squared. And the radius of that circle, which is sitting up here, is the height of that rectangle, which is square root of sine. So it's square root of sine squared. In other words, just sine. Oops, sine of x. Okay? That makes sense? That is the setup for that integral, for that volume there. Okay, let's go ahead and finish that. The integral of sine, remember sine comes from cosine comes from sine. If I put a cosine there, differentiating cosine would give me a negative, so I need to stick that negative on there to be careful. And I'm going from 0 to pi. So I plug in pi, cosine of pi is negative 1. Cosine of pi is over here. Minus negative cosine of 0 is 1. So make sure you're being super careful with all those negatives. I've got negative negative 1 plus 1, so this is going to be 2 pi. That is the volume of this football thing. Okay? Good? All right, let's try another one. Again, I think the challenge is getting these set up. Obviously, we've got a lot of integration techniques, so we feel comfortable once it's set up. But it's getting it set up that's the challenge. Okay. All right, let's take the region bounded by y equals 2 minus x squared and y equals 1 rotated around the line y equals 1. Okay. So the first thing I'm going to do, again, is draw my region. So 2 minus x squared looks like this, negative x squared looks like this, and then if I go up 2, that region looks like this. Okay. Y equals 1 looks like this. And so the region that they're talking to me about is that right there, that region right there. It looks a little bit like this one. Not the same. It's a little bit like it. Okay, and you can probably guess that this is going to go, in terms of x, those intersection points are from -1 to 1. I'm not going to solve for those, but you can pretty clearly see that that's where those are going to intersect. Okay, and then I need to rotate this around the line y equals 1, which is actually this line right here. So what I'm going to do, let's go over here. Let's draw in the region. Oops. Try that again. So I just draw the region. I'm not going to draw the extra stuff. Okay, that's the region right there. And then I'm rotating around this line, y equals 1. So that means I'm going to see something down there too. So again, I imagine taking this region, flipping it 180 degrees around that line, and then I draw in parts of the thing that are going to come out three-dimensionally. So this one also looks like a football in a similar way to how this one looks like a football. Okay. So let's draw in a sample slice now. So if I were to slice this up vertically, there would be a sample slice, and if that sample slice got rotated over here, it would look something like that, right? Again, if I pull that out, that's a disk. So let's set up the volume now. Volume is going to be the sum, the integral, of each of these slices, so which is going to be an area times a thickness. And our thickness, again, here is dx. We'll look tomorrow at situations where we're looking at thicknesses in terms of dy. We'll get to that tomorrow. But in this case, our thickness is dx. And x is going to range from -1 to 1. And the area, depends on what this looks like. This is a circle, so the area is going to be pi times the radius squared. Now here's where you have to be a little bit careful. This is why we're doing this step by step. The radius here, this piece right here, which is this piece right here, which is this right here, is not the function. The function, y equals 2 minus x squared, that radius, if I were to use the function 2 minus x squared goes from the function down to the y-axis, right? So if you were to just throw into that radius 2 minus x squared, that's going to be wrong because you're using this as a radius. That's not the radius. The radius is this thing. And it's because we're not rotating around the x-axis. We're rotating around a different axis, around y equals 1. So the difference here is that this height, that height right there, is 2 minus x squared, but I don't want this region right here. In other words, this has a thickness of 1 all the way across. So my radius is going to be this whole thing, 2 minus x squared, minus pulling off this section, so I just get this part right here. So I don't want this 1 region right here. Okay, so I'm taking 2 minus x squared. Sorry, it's hard for you to see this. 2 minus x squared minus 1, that's going to give me that black part that is the radius right there, okay? So that radius is the radius that I want to square. So in other words, I want, 2 minus 1 is 1 minus x squared quantity squared. Okay, so what's critical, what's different about this problem is that this radius is, you don't just throw the function in there. You have to be careful that you're taking this whole thing minus the part that you don't want. And you would then do this integral by multiplying this out, right? You have to multiply out the 1 minus x squared and then work on the actual integral. So that's an integral that you can do. I'm not going to move on from there, but the key here is that if you're not rotating around the x-axis, but around some other axis, you need to make sure that the radius you're using represents that. So in this case, I don't want the whole function. I want the function minus this part, which is going to give me this piece here, which is what I used for my radius, the function minus 1. All right. Okay. Let's do another example here, and you'll see something different happen. Okay. Let's take a region bounded by y equals x squared and y equals x. And we're going to rotate around the x-axis. So we want the region bounded by x squared and x. Then we want to rotate around the x-axis. So let's take a second and draw this. Okay, so here's x squared. Here's x. So the region bounded by both of those together is this region right here. That goes from x equals 0 to x equals 1. This is one that we've seen before. So that's the region that we want. Then we're going to rotate that region around the x-axis. And what is going to happen when I do that? Okay, well, let's just draw the region first, so we don't have any of this extra information. We've got a straight part up there, and then a curved part down here. If I rotate this 180 degrees, we're also going to get a part with a straight part down here, and a curved part right there, right? So imagine we had a mirror. When you flip this around the x-axis, what's going to happen is this end is going to form a circle, and you're going to get something that on the outside is like a cone. It's going to have straight edges on the outside. But on the inside, there's actually an inside here, and it's going to be kind of curved. It's almost like a cup. You had this in your hand and you had it as a cup. The inside of the cup would be kind of curved, it'd be bowed out a little bit, curved in like that. You kind of see that? So that's what my volume thing would end up looking like. All right, so this part is circular right here in a three-dimensional way. So let's slice it and see what happens. So if we sliced over here first, got a typical region. That region's over here. If I rotate that region down here, it also shows up down there. When I rotate it around, what I get is not a circle anymore. What I actually get is what's known as a washer. It's also known as an annulus. So what you get here, because this doesn't go all the way down when you rotate around the axis, is that you've got some space here, and that space, when you rotate, shows up as a space on the inside. So we don't have a full circle here anymore. We have what's called, this is called an annulus. It's also called, some people call it a washer. Rather than a disk. The only thing that that's going to affect is my formula when I actually try to find the volume. Okay? So to do the volume now, volume's set up the same way. It's the sum of areas. It's the sum of the volumes of these slices, and the volume is area times thickness. Now my thickness is dx. So let's go ahead and add that in, and x goes from, dx way over here. X goes from 0 to 1. You can see that here, from 0 to 1. Now to get this area, the outside is a circle and the inside is a circle. So the area of a washer turns out to be the big area, of the big circle minus the area of the small circle. So it's the area of the big circle minus the area of the small circle. That's going to give you the area overall, this area right here. Okay. And to get areas of circles, we just need the radius. So the area of the big circle is pi times the big radius squared, minus the area of the small circle is pi times the little radius squared. So we just have to figure out what is that big radius and what is that small radius. And we'll be done. Okay. Well, thankfully, the big radius is this thing right here. See if I can get a different pen that works. This thing right here, which is this thing all the way to the axis, which is the height of, it's this function right here, y equals x. So the big radius is y equals x, so it's pi times x quantity squared. The small radius is this thing right here, which is this piece right here, which is this height. And that height is the smaller function, which the smaller function is x squared in this region. So that is x squared squared. Okay? The bigger radius is the higher function x, and the smaller radius is the lower function x squared. So overall, the volume of what I want here is the integral from 0 to 1, pi times x squared minus pi times x to the 4th. And that is an integral, again, that you can do. Since this is our last example we'll do today, let me go ahead and finish this out. And we'll do another example tomorrow where we have an annulus, where we have a washer like this, okay? Let's pull out the pi. The integral of x squared is x cubed over 3, 1/3 x cubed. Integral of x to the 4th is 1/5 x to the 5th. And I'm going from 0 to 1. So if I plug in 1, I'm going to get 1/3 minus 1/5. If I plug in 0, I get nothing. So our common denominator there is 15. So a third is 5/15. A fifth is 3/15. So 5/15 minus 3/15 is 2/15 pi. That is the volume of that curved cup cone thing that we created. Okay? So like I said, tomorrow there's no quiz, but we'll go over another example of an annulus or washer, and then we'll look at a few examples of doing this in the y direction instead of the x direction. And then we'll take a little extra time and we'll get some formulas for some other three-dimensional objects that you've seen before. You've even seen their volumes before, the formulas, but you've never seen where they came from, so we'll derive those here. All right? So we'll do that tomorrow. Have a great day, and I'll see you on Thursday.